Hello and welcome to the Dimensionless Corporation. We are currently the #1 made-up company for biomedical fluid mechanics. Come on inside and we'll show you the role that we play in the biomedical industry. This is Bob. Bob is one of our lead engineers specializing in organ-on-a-chip devices. Now you might be wondering what an organ-on-a-chip device is. To further understand this, let's first dive into the general concepts of fluid mechanics. Fluid mechanics is the study of the physical behavior of fluids and how they flow. A fluid is a substance that has no fixed shape and continually deforms under external forces and stresses. Simple examples of fluids are water, soda, and milk. But fluids are not just liquids, they can also be gases. The helium in these balloons is also considered a fluid. There are many variables that affect fluid flow, but the most important properties are density, viscosity, and pressure. Density describes how much space the fluid takes up in relation to the amount of matter within the fluid. Viscosity is the property of a fluid that describes how fast or slow it will flow. We can think of thicker fluids like peanut butter and honey as having a higher viscosity and flowing slower than fluids such as water. Pressure is defined by how much force is pushing on a fluid and is generally given as the force over a given area. Each of these properties contributes to the fluid velocity profile and altogether will define how a fluid will flow in a given situation. Will the fluid be at rest like in this calm and peaceful lake? Or will the fluid flow chaotically like in this picture of Niagara Falls? This concept can be divided into two types of velocity profiles for fluid flow. Shown in the top graph, laminar flow is when the fluid flows smoothly in a one-dimensional direction. When flow is not laminar, or when it flows irregularly, the fluid is considered to have a turbulent flow. All this information about fluid mechanics is interesting, but why exactly isn't it so important? At the Dimensionless Corporation, we research these basic principles of fluid mechanics and apply them to the fluid flow within our bodies. The human body is composed of many fluids. The most obvious examples are the blood flowing through our circulatory system and the air flowing in our lungs. These fluids play an important part in human biology and have a critical role in keeping us alive. For this reason, you can see our scientists are hard at work researching how properties like density, viscosity, and pressure affect the fluid flow in our bodies. For example, blood pressure is the force exerted by the blood against the walls of the blood vessels. This pressure depends on the work being done by the heart and the resistance of the blood vessels. A healthy person should have a blood pressure of around 120 milligrams of mercury when the heart beats and around 80 milligrams of mercury when the heart relaxes. High blood pressure is a common and dangerous condition. Over time, if untreated, it can cause health conditions such as heart disease and stroke. From what we've learned so far, Bob is now trying to come up with ways to reduce blood pressure for patients who need it. It turns out that eating healthy and exercising regularly are key factors that prevent high blood pressure. But there are also medications that can be designed to reduce blood volume in order to then reduce. Other than blood pressure, blood viscosity is another important property that affects blood flow throughout the body. Blood is considered to be a non-Newtonian fluid. This means that the viscosity of blood changes depending on how much stress or force is applied on it. The reason for this changing of viscosity is due to the composition of blood. Blood is made up of three primary types of cells known as plasma cells, white blood cells and platelets, and red blood cells. As blood flows through our circulatory system, it is constantly picking up oxygen, glucose, and many other molecules that we need to keep our body functioning. This means that the composition of our blood might be different before and after eating. Because of this, calculating the expected fluid flow for blood can be somewhat complex and difficult. Luckily, our engineers have a deep understanding of fluid mechanics and can approximate blood flow very accurately. With these approximations, Bob can then calculate many different important characteristics of blood flow within the body. For example, he might calculate how quickly a specific drug diffuses into the bloodstream. This information is very important to biomedical engineers, healthcare professionals, and patients. Thanks for stopping by the Dimensionless Corporation. We hope that you learned a thing or two about biomedical fluid mechanics.